Dear students, in the last lecture we derived the Euler's formula using the Taylor series. In this lecture we derive the Euler formula without Taylor series. First of all, we take a complex number z is equal to cos theta plus iota sin theta in equation 1. If we differentiate with respect to theta, then dz by d theta is equal to minus sin theta plus iota cos theta, which can be written as iota cos theta, and we replace minus 1 with iota square. After taking common iota, it becomes iota cos theta plus iota sin theta. You can see that from 1 we can replace it by z, so it becomes dz by d theta is equal to iota z. Now we separate the variables and it can be written as dz over z. We divide this z here and multiply d theta here. So after integration we get ln z is equal to iota theta plus some constant, say c1. In the next step, taking exponential function on both sides, it becomes exponential ln z is equal to exponential of iota theta plus c1, which can be written as exponential of iota theta into exponential of c1, which is also a constant, say c. So from equation number 2 we can write equation number 3 as it becomes z, and it can be written as z is equal to c exponential of iota theta. Now here we find the value of the constant c. We take a special case theta is equal to 0 and put in equation 1. When we put theta is equal to 0 in 1, it becomes z is equal to cos 0 plus iota sin 0. Cos 0 is equal to 1 and sin 0 is equal to 0, so we can obtain z is equal to 1. Then we put this z is equal to 1 in equation number 3 and theta is equal to 0. So the value of c can be obtained as c is equal to 1. Now we replace the value c is equal to 1 in 3. It becomes z is equal to exponential of iota theta. You can see that in the first equation we take z is equal to cos theta plus iota sin theta. So from equation number 1 and 4 it becomes exponential of iota theta is equal to cos theta plus iota sin theta, which is the Euler formula.